A quick look at my gun collection would show you that I'm mostly a black powder cartridge shooter. So my bullets are generally made of simple mixtures of tin and lead, and hardness hasn't been an issue. But lately the subject came up in the club, so I thought I'd have a go at making a hardness tester using bits and pieces that I've got lying around. The simplest and most common test for lead hardness is called the Brinell test. In this test, a steel ball of known diameter is pressed against the test surface with a known force. If you know the diameter of the steel ball and the applied force, and you can measure the diameter of the indentation made, you can calculate the Brinell hardness number, or BHN. This is the Brinell equation. The inputs are applied force, indenter ball diameter and indentation diameter. It's quite convenient to punch it up into a Microsoft Excel spreadsheet as a convenient way of working out your results. If solving equations doesn't turn you on, there are a number of online calculators which will work out the results for you. This is a particularly nice one because it allows you to use different units, so you can use foot, pounds and inches if you're in the United States, and kilograms, force and millimeters if you're in Europe. If all goes wrong, you can of course just order a bottle of Prosecco from Tesco's and take it from there. Of course, if you don't want to make your own hardness tester, there are a number of models already on the market. This particular one is the Lee. It's very popular, relatively inexpensive. It uses a spring mechanism to apply the force. This is the Seiko. I believe this is one of the more popular but also one of the more expensive of the testers available. This is the LBT, and as far as I'm aware it's the only tester on the market which claims to measure Brinell hardness directly. And here we have the cabin tree. This uses a spring and a screw mechanism to indent the test sample. Nearly all of these testers actually use a reference sample, and the reference is normally pure lead, which is usually agreed to have a hardness of 5, although there are some schools of thought that now believe that it's probably nearer 4.5 than 5 for 100% pure lead. If you've been looking up the Brinell hardness test on the internet, you might be thinking that you're going to have to need a ball diameter of 10 millimeters and a force of 3,000 kilograms. Well, that's clearly something which we can't reproduce in our home workshop. But if you look more closely at the standard, what it actually says is that although the ratio of the diameter of the ball to the applied force for steel is 30, if you look at lead and tin, it's down at 1. What this means is that we can actually use a much smaller ball and consequently a much smaller force, which makes the whole thing much more manageable. So here, looking at this chart here, these are conditions for steel and cast iron, very high forces and a 10 millimeter ball. But down here, where we've got the force to diameter ratio of 1, we can use 61.29 newtons, which is about 6 kilograms force. This makes the whole thing infinitely more manageable for the home user. I'm going to base my Brinell tester on a loading press. This particular one is the RCBS Rock Chucker, but most loading presses will be suitable. And what I'm going to do is mount the test piece on something placed in here, some sort of anvil, and then I'm going to apply a force to it down through here using a dead weight system. These are some of the other bits you're going to need to make this. Something like this would be very useful. This is a Lee push-through sizing die. We can use this part as our anvil to hold the specimen, and we can use this part to support the rod which carries the weight system. So you're going to need this, and you're going to need a bit of rod which is going to go down through the centre. If you can't find a bit of rod that fits exactly, you're either going to have to turn down the rod or bore this out. If you don't have one of these lying around, you could get one of these. This is a blank die which you can use to make dies of any size you like. So you would need to bore through this right through the centre, maybe cut it off because you don't really need the full length of that. What I'm going to do is use this. This is an adapter which fits on the press. This unscrews. And this goes in the top. And what I've done is I've fitted a linear bearing in here so that it gives a nice smooth passage for the rod. Another thing you'll need is a platform to hold your weights, which fits on top of the rod. This particular one is made out of a piece of 16" square aluminium, or aluminum if you don't speak the Queen's English. And finally, you're going to need some lead. Now if you're a hand loader or caster, you may have lead in this form, the ingots that are cast up in the Lee mould, or you're going to have lead in some sort of form. I'm lucky and I've got these larger bits of lead which weigh about 4 kilos each. Once we've got all our parts together, we can assemble them onto the loading press. What we have here is the anvil, which if you remember we took from the Lee push-through die. This is my weight table, the shaft. I fitted a collar on it to limit the movement of it, and I don't know if you can see this in close-up, but what I've done here is make a detachable ball probe. This is because this is still experimental and I don't actually know which size ball would be best. So I've used a piece of 6mm rod which fits into the main shaft and is held in by the scrub screw, and on the end is the ball, which is mounted with a dab of JB Weld. This particular ball is 3mm. So the weight table just drops into the linear bearing like so, and we can add our weights. Of course you need to know the mass of all the moving parts, including the weight table and shaft. And for this particular test I have a total mass of just over 10 kilos. Right, let's run some tests. Round nose flat point bullet's the best. If your bullet doesn't have a flat point, then you need to fire a flat on it. This is round nose flat point pure lead bullet, which is used in my Ruger Old Army pistols. So that just fits onto the anvil like so. Then apply the weight by just pulling down on the lever and lifting the weight table. Allow a set time for the test to take place, say 15 seconds, then let it down, remove it, and there you go. So that's pure lead. This bullet is a hard cast 45 caliber bullet, which is claimed to have a Brinell hardness of 15.5. That goes on there, and again lift up the weight table, wait for the set period, say 15 seconds again, let it down. Okay, that's the test. Here are the two bullets we just tested. The pure lead one is on the left, and I think it's fairly clear that the indentation on that one is wider than the indentation on the hard cast bullet. All we need to do now is find a way of accurately measuring the diameter of those indentations.
This is what I use for measuring the indentations. It's a Chinese USB microscope with 2 megapixels resolution and a claimed magnification of 1,000 times, although I somewhat doubt that. You can buy these on eBay for £15 or less. I actually bought mine from Amazon for the simple reason that if you get a problem with them, Amazon will just replace it free of charge and very quickly. And sure enough, the first one I had lasted 4 days before it stopped working. So, okay, it's sometimes worth paying a little more. Most of these microscopes come with some sort of calibration ruler, and something like that is essential to calibrate your measuring system. But at a push, you could use a steel rule.
Measuring the indentations is a two-stage process. Firstly, we have to photograph the indentation itself. Then we have to photograph the calibration graticule in the same plane as the indentation. So what we do first is put our calibration graticule and white card there, and then place the bullet to be measured underneath, like so. Adjust the focus until we get the clearest picture, do there, and then just click on photograph snapshot, like so. Now we have a snapshot of the indentation of the bullet. Now we need a snapshot of the calibration graticule, and to do that we remove all this and put 4 of the same bullets on there like that. Now just to support the calibration graticule on the white card, and then by moving the graticule around, so, check the focus again. Now those white spots are the LEDs attached to the microscope, which are a bit annoying, but we can reduce them somewhat. Okay, take our snapshot. Okay, now we have a snapshot of the calibration graticule as well as the indentation.
Okay, now we're ready to start measuring our samples. We'll start with the pure lead one. This is the calibration graticule for that. The first thing we need to do is calibrate the measuring system. So to do that we go to Microscope, Calibration, and the red line appears on the screen. Now here we have a total traverse of 9 millimeters. So what we can do is move that end of the line down to there, move this one along to there. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 millimeters. And in here we'll measure in micrometers, thousandths of a millimeter. So we put 9,000 in here. 9,000. This is our 9 millimeters translated into microns. Click on OK. Right. Now we can load the image of the indentation. Go to Device, Import Image, Pure Lead. Okay, there's the Pure Lead image. Now there are two ways we can measure this. We go to Measure, and we can either draw a line across the diameter, right there, like so, and this will come up with 1363 microns or 1.36 millimeters, and we can do that several places. Or the other thing we can do is erase that and draw a circle, like so. Draw a circle and fit the circle inside the indentation. Move it over a little, make it a little bit bigger. And so, and there we already have a diameter of 1282 microns or 1.282 millimeters. And we just need to make a note of that to enter into our calculations. Completed all our measurements, we can enter them into the Brinell equation. And what I've done is put the Brinell equation into a Microsoft Excel spreadsheet for convenience. But of course you can use one of the online calculators if you prefer. So here we're going to input data for pure lead bullet, a 4440 commercial bullet, and a 45 caliber bullet that's claimed to have been cast from Lyman number 2 alloy. So the ball diameter we used is 2.5 millimeters. The load used is 7.076 kilograms. Right, the indent for pure lead is 1.282. Gives us a BHN of 5.1. For the 4440 bullet, it's 0.864. Gives us a BHN of 11.7. And for the Lyman number 2, the indent is 0.763. Gives us a BHN of 15.1. So if you've managed to stay awake so far, you might be thinking that this is a kind of complicated method, but actually it takes far longer to explain how to do it than to actually do it. And with a bit of practice you can process lots of bullets in quite a short time. So what are the advantages of my system over others? Firstly, and I think this is most important, it's a direct method. It doesn't rely on springs or screw threads, and most of all it doesn't rely on a reference sample. Secondly, it's low cost. You could probably make a system like this for less than anything you could buy on the market currently. And finally, if you make one of these, you end up with a digital microscope that you can use for a whole lot of other fun projects.